All right, so taking all this now and apply it to an atom. Or more precisely, let's apply it to the electrons that are whizzing around the nucleus of an atom. Right? How do we actually formalize this? How do we actually write down the equations and that sort of thing? So we're going to step through the development in a very hand-waving sort of way here because we're not going to the math. The math is very complex on this. It's really the subject of a senior level or even a graduate level course. Right? But we could talk about it and understand it, and that's what we need to do at this level here. Let me shrink this down. There we go. All right, the first one, first person we should talk about is Schrodinger. Ernst Schrodinger. His contribution is essentially recognizing that yes, electrons are three-dimensional standing waves, which we can symbolize by the Greek letter psi, capital Psi. Well, you can use lowercase as well, but anyway, psi is called the wave function. So just like f of x, a function. This is a function. If you were to plot it out, it's a wave. It's going up and down, up and down. Right? But it's specifically, it is the wave that fits around an atom. It's the wave that the electron will behave like. Or if you want to interpret it a different way, we say the electron is this standing wave and psi is the equation for it. If we plotted it out in 3 dimensions, we'd see what this electron looks like. Okay. Now, how do you actually get psi? How do you actually get what is that equation? You would solve what's called the Schrodinger equation. We're not going to do this, but again, this is just the background for you to begin to understand quantum mechanics. This is called the Schrodinger equation. This is an operator. It's called the Hamiltonian operator. H working on psi equals E times psi. Very briefly, again, you're not responsible to know this, but very briefly, the Hamiltonian operator, when you operate on a wave, in this case psi, the wave function of this electron, it gives you the total energy. In this representation of quantum mechanics, that gives you that total energy E times psi, the wave function right back. So a constant times that. Very confusing. Again, we're not going to even begin to try to look at that kind of math at this level. Right? But the important thing here is that this is an equation that if I correctly put in the Hamiltonian, which would include the operators for kinetic and potential energy of all the different things that make up an atom, especially, I guess, the nucleus and every one of the electrons around it. If I design that Hamiltonian correctly and I write this equation out, so it's a big nasty equation, and then I try to solve it to say, hey, what wave satisfies this equation? What wave actually works? Right? This is just the formal way of saying that. Like, you got the guitar string, what waves will fit in that region? Okay? This is the equation, the Schrodinger equation, which you would solve to answer that. All right, so the wave functions of electrons are found by solving the Schrodinger equation for that atom. Okay. Now, a helium atom would have a slightly different Schrodinger equation than a hydrogen atom. Why? Because you got a different charge of the nucleus. You've got 2 electrons instead of just 1 electron. The conditions are different. Okay. All right, Max Born. Max Born came along and interpreted for us how we should think about this wave, the psi. Right? His take was that, hey, you know what, these electrons, they're still particles. Remember, there's this dual nature, right? They're still particles, but you could think of them as where those particles are located. It's kind of like saying if you got a wave of water, it's going up and down and up and down. I said, hey, you know what, water is still a particle. I got an H2O. It's just where is it located? Sometimes it's up, sometimes it's down. It's in this wave, right? It's not a perfect analogy, but it'll get you there, right? It's not bad. So the wave is just telling you the probability of where you might find that electron if you consider it a particle. Okay, that's a perfectly good interpretation. Now, how does that fit in to the Schrodinger equation? We solve the Schrodinger, we get psi. Now, it turns out with the wave mechanics, if you take the absolute value of psi and square it, you get what's called the probability density. This is like normal, like a mass density, grams per, say, milliliter. If I multiply by volume, milliliters, then I would get the actual mass, right? Well, this is probability per milliliter, or this is probability per volume. If I multiply by the volume, I'll get the actual probability of this electron being at these various locations in 3D. And so that's what this next line is here. If I take that probability density and multiply by delta V, I get the actual probability of where that electron could be. Again, background information. I want you to just get a sense that, hey, we're not just making up these waves. They're not just coming. They actually come from theory. Very carefully worked out theory. Very difficult theory as far as the math is concerned, but very well established. Okay, very well established. So theory, we solve it, we get the wave function for, say, a hydrogen atom. You go through it. It's a lot of math to actually see that solution. We do it with our seniors in chemistry. They do it in physics as well. Like I said, it's well known. You can get the actual function for psi for the electron in a hydrogen atom. We don't need to look at that what function. We don't need to see what it actually looks like. The big important thing for us, which you are responsible for, is the fact that if you look at that equation for psi, three things pop out at you. Three things being the three quantum numbers that show up as part of that equation. Remember how we had the guitar string and we said only multiples of a half wave would fit in that guitar string as far as a standing wave is concerned. And so we could say, hey, n equals 1, 2, 3, 4, etc., etc. And then for the circular standing wave, n equals same thing. Now we have very complex waves. We have very complex size, but they are the ones that fit in this region around an atom, around the nucleus of an atom, I should say, to make up the atom. Where is that electron? What does it look like? Right? And that equation for psi has quantum numbers in it, just like the other ones that we looked at. So in a way, that's not surprising. It makes perfect sense. The psi's have quantum numbers in them. And of course, we also saw that once you get a quantum number, then we're talking about quantized energy as well, because each one of those psi's, each one of those waves, has a corresponding energy. Right? So we've got quantum numbers. What are they? The quantum numbers are n, just like before, and it equals 1, 2, 3, etc., etc. Okay. Another quantum, and I'm going to talk about the interpretation of it here in just a second. The next quantum number is L. L is called the angular momentum quantum number. L, it doesn't equal 1, 2, 3, 4 like n. L actually starts at 0, and then it goes up 0, 1, 2, 3, but it doesn't go up forever. It actually goes up to n minus 1. So if I have a wave, I could have n equals 1, n equals 2, n equals 3. Let's take the wave that had n equals 3, let's say. What other quantum number is in that equation? Well, L is, and for that, L could equal 0, 1, or 2. It can go up to, again, n minus 1. So if n equals 3, then L could be 0, 1, or 2. If n equals 5, L could be 0, 1, 2, 3, or 4, etc., etc. So the limits on L are actually governed by the first quantum number. The third quantum number is m sub L, the magnetic quantum number. The m sub L equals negative L through 0 up to positive L. Right? So here we've got a range as well. If L is, say, negative 1, then m sub L could equal negative 1, 0, or plus 1. Right? So that one's dependent on L, and L again is limited by what n is. So we've got these quantum numbers that are interrelated, dependent on each other in a very specific sort of a way. Now back to the interpretation a little bit here. N equals 1, 2, 3. Principal quantum number. We think of the interpretation of that one as being the energy level or the physical shell that electron is in. Right? So if I have the nucleus right here, if n equals 1, it's kind of located in this region fairly close to the nucleus. If n equals 2, that wave is located in a further region from the nucleus. If n equals 3, further yet, way out here. Okay? The larger the n is, the larger the shell that you're going to find that electron. Okay? Just further away. And remember we talked about before, as you go farther away from the nucleus, your energy goes up, right? And so as you go farther away, the energy also goes up. And so we think of it as the physical shell, the distance, and the energy level that that electron is going to have. So that's n, the first quantum number. L equals, again, 0 up to n minus 1. L is thought of as the shape of the wave. As we go through and look at the solutions, look at what these sizes actually look like and plot them out in 3 dimensions, right? We get very different shapes that are popping up. L tells us what that shape is going to be, right? The easy shape would be just a sphere, just a ball, okay? And that's exactly what you get with L equals 0. The second one, L equals 1. Maybe you got a quantum number of 3, so L equals 1 would be perfectly okay, right? L equals 1 looks like a dumbbell. Kind of has a blob out here and the nucleus in the middle and another blob, or 2 lobes, if you will. Of course, a sphere only has 1 lobe. A dumbbell has 2 lobes, so it doubled the number of lobes it has. For L equals 2, climbing up here, if L equals 2, it has 4 lobes. They look like kind of a clover leaf, more or less. L equals 3, 8 lobes. Kind of doubles each time. Now, it's not strictly true. Some of them, the lobes are combined, and so they look more like a ring, perhaps. These are very complicated waves, but more or less, it's just telling you the shape, and the shape has lobes that more or less double every time. Because the shape is a very intuitive sort of a thing, we can think about it, we can see it even in our mind, then this shape, we don't just call them L1, 2, 0, 1, 2, 3. They're called S, P, D, F. A spherical one is called an S, a dumbbell-shaped one is called a D, the one with the 4 lobes is a, P. The one with the 4 lobes is a D, and the one with the 8 lobes is an F. And I'm going to show you pictures here in just a second. So the shape of them, the shapes have actually just names, they're just single letter names, but they have names, and that's a little easier to talk about. Okay. Finally, the M sub L down here, remember it goes from negative L to L. That's thought of to represent the orientation. Now, a sphere, you can rotate the sphere this way, along the X, along the Y axis, and it kind of looks the same because it's got perfect symmetry. So there's no multiple orientations to speak of with that one. But think of a dumbbell, right? A dumbbell, you could have, the lobes coming out here and here. So this pen, I could locate it along my X-axis, orient it, I should say. I could orient it along my Y-axis. I could orient it along my Z-axis, right? This kind of way. And so there's different orientations that I could put those in. The M sub L quantum number relates what its orientation can be. All right, some pictures are going to really help here, which we're going to get to in just a second, I promise. First of all, let's take a look at the collection of quantum numbers then that we might have for these electrons in these atoms. Remember, these quantum numbers are from the solutions of psi, so in a sense they are describing what the waves of these actually look like. N starts with 1. So if I'm close to the nucleus, principal quantum number is 1. I'm close to the nucleus, I'm at the lowest energy level. What could L be? Well, L starts at 0 and goes up to n minus 1. Well, n minus 1 is 0, so the only one that's possible is 0 itself. So if my electron has a quantum number of 1 for n, it's going to have an L of 0. And M sub L, remember, it goes from a negative L up to a positive L. So what, negative 0 to positive 0? 0 is the only one there. Right? So 1, 0, 0. There's a set, a collection of quantum numbers that an electron might have. Okay? Remember, 1 is the principal. If L equals 0, right up here, if L equals 0, that's what we call an s orbital, and it's going to be kind of spherical shaped. And so I'd call that a 1s. All right. Let's move up to the second energy level, or the second principal quantum number, n equals 2. Now for that, L could either be a 0 or a 1. Remember, L always starts at 0 and it goes up to n minus 1. In this case, 2 minus 1 is 1. And so L could be either a 0 or a 1. And if L equals a 0, where did that extra little 0 come in? I got this on my notes here. Oh, and I just totally erased it. Let me back that up. Okay. Anyway, if L equals 0, then M sub L has to be 0 only. Ignore this little extra 0 there in the middle. If L equals 1, then I could have an orientation of minus 1, 0, or plus 1, or 3 different types of orientations. Okay. Now, an L of 0 is an s orbital. an L of 1 up here we said was a p orbital. So and because they're both part of the second level in this case, I would call it a 2s or a 2p. And the three orientations of those two p's, I could call it a px, a py, and a pz if it's along the x-axis, the y-axis, or the z-axis. Okay. Sometimes we indicate these orbitals just by a little line and we show how many there are. So I could have the orbital called 1s, the orbital called 2s, and then three different ones that would be called the 2p level. Because again, px, py, and pz. Go up to the third level, now L could be 0, 1, or 2. And so this would be a 3s. I see my 0, and that kind of got moved up and bumped up and down a little bit. So that's what happened. All right, anyway, 3s, I could have the 3 p's, or when L equals 2, the 3 d's, like that. Now, if you got 5 orientations for the d orbitals, right, from -2 up to +2, 1, 2, 3, 4, 5 of them, 5 different ways I can orient it in 3 dimensions. I can't simply call that then p dx, dy, or dz, because that's only 3. I actually have 5 equally sort of orientations in the full 3-dimensionality to talk about there. And so that's a little trickier. They do have labels. You don't have to worry about these labels, but like 3D xy, 3D yz, here's the xz, x squared minus y squared, or 2z squared. So these are just the labels that they give for the 5 different orientations. What you need to know is that there are 5 of them. The S has 1 orientation, the only one possible. P's have 3 orientations. D's have 5 orientations. And so again, if I was to draw this just as like a little line, little thing to fill my electrons in, here's my 3s, my 3p's, and my 3d's. If I go up to the 4th one, now I can go all the way up to the f orbitals, and the f orbitals have 7 different orientations. So there they are. So you can see how I can just keep building and building and building, getting bigger and bigger as far as these waves and the size of them, and again the distribution, or where they are, if you will, about the nucleus. What do the wave functions actually look like then? We've started to describe them already as kind of spherical or dumbbell shaped. The book has pictures of what they look like, and oops, sorry, my thing jumped there. And so here's their picture of an s orbital. More specifically, the 1s, the first one here, the second one here, and here's this profile. Here's the 2s. Here's the third one. This is the 3s. Now remember, 1, 2, 3, those are the principal quantum numbers, so we're talking about closer and then further out from the nucleus. The 1s wave, sometimes they call these orbitals. They're not orbits, but they're kind of like they're going around the nucleus. Orbital, AL there is the name of it. So an s orbital, or a 1s orbital, 1s wave, is going to look something like this. If you look at the probability of it, the probability, well, it's 0 at the actual nucleus. We can't be right on top of the nucleus, but then as you go away from it, you see the probability goes up quite a bit here. It peaks, it maximizes out, and then it falls off and stays down. And so if you think about that, here's my nucleus. As I go out from the nucleus, all of a sudden I start getting more and more probability of it. I reach some maximum probability, and then so it kind of goes up. And then as I go further out, it peters out, and I get back to almost 0 probability as I go away from it. So it's got this area out there that's thicker in probability, or in other words, that's saying that's where the wave is. That's kind of like saying an ocean wave, hey, it goes up and it's thick there, and then it goes down, right? It's the same idea, the probability of where do you find that electron. Okay, and so the book just has this little blue dot here. Essentially what that is it's kind of like a beach ball. It's a hollow sphere. The nucleus is in right in the middle. And then as you get near the edge of that beach ball, the probability goes up, and then it falls back down as you go on the outside of the beach ball. So you get this shell, this round ball, hollow ball, that goes around the nucleus, and that would be called the 1s orbital. The 2s orbital has a double probability sort of thing, a minor kind of inner wave, and then a maximum that's a lot farther out. If you look at here, the X scale here is in picometers. This one goes, I don't know, what is it, about 5 something like that, 510 picometers is where it's that's called the Bohr radius, by the way. It's about 5 picometers is about where it maxes. Where this one, hey, that second big maximum out here, I don't know, maybe 39, 40 picometers. I'm looking at the x-axis there. All right, and so again, it's further out. It's got this minor little bit in the very kind of close, very near where the 1s orbital was, but the 2s orbital, really most of it's way out here in a larger distance away from the nucleus, right? And so here's their picture of that. It's kind of cut away there so you can see it. That inner little peak there is in blue, and then the outer one is the red or the pink one here. It's kind of like a beach ball inside of a beach ball, but the outer beach ball is where the by far the greatest probability exists, and so that's where we'd say for the most part that electron is. That wave looks like a big hollow beach ball, but there's a small component on the inside, a beach ball inside of a beach ball. A 3s orbital, now we got 3 of those, and so a beach ball and a beach ball and a beach ball kind of a thing. But again, it's that outermost beach ball, and this one now goes out to way out here. You're talking about almost 75 picometers away, so further out yet. That's where most of its electron density is going to be. Okay. And we have these nodes here. Of course, there's no node here in the 1s, but you look at the 2s wave, and there's that node right there, right between the two peaks, right there where we got 0 probability of the wave. The 2s has 1 node, the 3s has 2 nodes now between exactly those two peaks. And so those nodes are actually where there's 0 probability of finding that wave. Right? These waves of these electrons, they go up, they go down, they go up, they go down, kind of a thing. And those nodes in between, we're saying, hey, you never find them there. They're just not shaped that way. These waves aren't. And if you think about an electron, where's the probability of finding it? You've got a small probability of finding it in this inner region or this middle region, but by far, your highest probability of finding a 3s electron would be out here in this region, further away from the nucleus. You can always calculate the number of nodes in any of these orbitals by this very simple equation, n minus L minus 1. So for this, for example, the second one here, the 2s, n would equal 2. L is 0 for an s orbital. L always equals 0, and then you get that minus 1 in the end. So 1. There's 1 node, and sure enough, that's what we see there, 1 node. Okay. To actually look at this better, there's this really cool program, and let me pull it up here, called Orbital Viewer. It's actually, this one's got a copyright way back in, wow, from 97 to 2004 by David Menthe. But this is a really cool program to actually see what these orbitals look like. And so what I'm going to do is I'm going to change this to a 1s orbital. Okay? This is what it would look like. There it is. And so let me zoom in on it here so we can see what's happening a little bit. Fuzzy, right? This is a probability. It's not like we're sure exactly what it is, but it's mostly just a sphere, spherical shape probability for a 1s. Makes perfect sense. Now if I switch this to a 2s, remember the 2s, so we go up to the 2 level here, we said it's like a beach ball inside of a beach ball. And so here it is. We got this much larger, first of all, you can see. I didn't change the scale yet. This one goes all the way out here. And then we got this orange kind of in the middle. They're showing the 2 different humps, essentially. Let me zoom out here so this is a little easier to see, perhaps. All right, so you got this inner one and this outer one. But again, if I rotate it around, it looks the same in all directions. This is a sphere inside of a sphere. And one of the things I can do with this program here is to cut out a little wedge so we can see that better. So I just cut out a little wedge here, and you can see there's the inner sphere, here's the outer sphere going around here, and right between there's that node, that nodal surface where we're not going to have any probability of finding that. All right, so let me go to the full one again. A sphere inside of a sphere. Let's go up to the 3s. So a 3s orbital, a sphere inside of a sphere inside of another sphere, right? And so you can see that again, the orange and then this blue and this bigger orange here looks pretty much exactly what you'd expect. A sphere, and again, if I rotate it, perfectly spherical. It's the same no matter what. Let's go ahead and cut a wedge out here just so we can see that. Here it is, and if I rotate it around this way, there you go. Here's your inner sphere, your middle sphere, and your outer sphere, and the 2 nodal regions between the spheres. All right, cool. So that would be what a 3s orbital looks like. Let's move on. p orbitals. Now we said those were kind of dumbbell shaped, right? P orbitals, L equals 1. What do they look like? Well, here's the book's picture of them. They're a dumbbell shape. So kind of on the x-axis, this would be called the px orbital, and you go to the negative axis and the positive x-axis, and there's a nodal region you can see right in the middle there. Okay. Here's the py and the pz. Again, a dumbbell type of a shape, just going along the different axes. Get a better picture of that, let's go back to this program and pull up a P1. Now the first time you find a P is in the second level, not the first level. It can't exist in the first level. The first level only has an S, if you remember that chart we did. But the second level has both an S and a P. So we'll put a 2 in here, and let's put a P in here and see what that looks like. Well, there we go. They're just like what the book shows. We have our dumbbell shaped to the left and to the right, and that node right through the middle there. If I can zoom in on it, again, the left and the right, the two sides, and the node right in the middle. Now this one is not perfectly symmetrical because it's got those two dumbbell shapes. And now up and down, you see, I mean, you rotate it, they are kind of like spherical nodes as you go out there, right? Or spherical lobes, excuse me, and that one node right in the middle. Okay. What happens if you go to the next energy level out? So that's a 2p one that we're looking at here. What if we go to a 3p? We know it's a p orbital dumbbell type shape, but it's bigger, it's way out there. Well, just like say the 2s was like a beach ball inside of a beach ball, it's kind of like a small s inside of a bigger s orbital. If you go out to the next energy level for this, it's going to be like a small little p orbital inside of a bigger p orbital. That's exactly what we expect. So this is a 2p. Let's do that. Let's go up to a 3p orbital. Okay, we can see it's much bigger, and you see we have this little p orbital here inside of this bigger one. Yeah, let me zoom out here, you can see that a little better like this. So here's kind of like the little 2p, but here's what we get in additional when we add the 3p. Now by far the most highest probability is out here in these outer regions. Well, it is the 3p, it is the greater, the next up principal quantum number. And so, yeah, it's bigger, definitely further from the nucleus, but it's got these little minor regions in the middle right there. And if I rotate it, now here's looking at end on, and here's the other way again. So you see it is dumbbell shaped, but it's just bigger. And it's got this little minor one inside of the bigger one, just like the beach ball inside of the beach ball. And again, I could cut this away, take a wedge so we can perhaps see what the cutout looks like. So let me just go around here. Here's the left side of the inner P and then the outer P and that nodal region right between it. Alright, so there's a 3P. Let's go up one more just so we can take a look at something a little more complex, a 4P. And you probably guessed it. It's like a P inside of a P1 inside of an even bigger P1. So there we go. It's just one inside of the other. It's still dumbbell shaped. And this trend is just going to continue on and on and on. Okay. Let's get this way. The d orbitals. Here's the book's view of the d orbitals. For the most part, like I said, they have 4 lobes. So the s has 1 lobe, the p's have 2 lobes, the d's have 4 lobes, doubles each time. And so there are 5 different orientations of that. We talked about that before. The s, that increases by 2 each time. So the s has just 1 orientation, the p's have 3. The d orbitals have actually 5 orientations. And there's those labels I mentioned before of what they are. Right, so this would be like the 3dxy, the 3dxz, etc., etc. And the orientation is given by that ml quantum number, -2 up through +2. So there's the book's picture. Again, let's go back to this program here and take a look at that here. The first D I find is in the 3 level. And so there we go, a 3D. And let's just take a look at that. Actually, that's not the one. Let me back this up to the different orientation. There we go. That's the one I want. Here you see the 4 lobes kind of going out like that. Okay, so that would be a 3D. Now there is one of these, and some of them are loaded in the XY, YZ, XZ plane. I mean, you got all these different orientations, and you see that's what these are here. You see there is one right here, which just the different orientations, this ends up being primarily along the z-axis with a little bit, instead of a lobe, it's got this kind of like this double lobe, which a ring kind of is the same as the double lobe essentially. Anyway, it looks a little bit different when you actually plot this out, but hey, when you solve the Schrodinger equation, here's the size, and this is what it's predicted to look like, and so there it is, kind of an odd one, and that's what this orientation over here is, instead of the 4 lobes, if I go to m sub L of 0, it's showing you that one with the ring right there. Okay, but that is an actual d orbital. I like to think of most of the d's orbitals as having those 4 lobes though. And finally the f's, well, if there are 5 orientations for the d, then there's going to be 7 orientations for the f, and for the most part they're going to have 8 lobes, again doubling it. Or you get this 2 lobes with this double ring structure like this. Here you actually get 6 larger lobes, if you will, and so they get very complex once you get up this high. Alright, but we can take a quick look at that as well. Why not? The first time we're going to see a f orbitals is in the 4, so the 4f, there it is. That's the one with the double ring going around it. Let's see if we can get one of them with just the 8 lobes. There you go. Actually, this is the 6-lobed one. No, this is the 8-lobed one, where you've got 4, if I do it this way, 4 of them going to the left, 4 of them going to the right. You can see that. Hopefully you can see that. There's the 4-fold symmetry if I turn it this way. And that's a total of 8 lobes going around. Right? It gets pretty complicated and difficult to see for sure. Right? Of course, what do these look like if I go to a higher energy level? Then it's going to be an F inside of an F, just like the other ones corresponding. It all works out the same. It gets very crazy looking if you try to actually put those all together. Okay, so that's what they look like. Right? They're waves. They're waves with highs and lows, but they're fit around the nucleus in that space of an atom. And it's kind of amazing when you think about it then. The quantized energy that Bohr saw, the quantized energy, that Rydberg and Balmer that they saw, and then Bohr made his model from that, right? That comes from the idea that only certain waves will fit in that space. And when I look at the equation for those waves, hey, they've got quantum numbers in them. And it all comes back to then this idea of quantizing the energy levels due to the only allowed waves that fit in that space. If this is hard to grasp, again, I fully understand. It is hard to grasp because our macroscopic world just doesn't look like this. Okay? But on the microscopic world, it's the reality of things down there. Nodes. We talked about how many nodes something has, right? The nodes are actually pretty simple. The nodes start here for an S. We didn't have any nodes at all for the S, but then we had one node between the inner and the outer beach ball for the 2S. Then we had the 3S, which had 2 nodes. You can see it just kind of increases the number of nodes by 1 every time you go to a higher energy level. Right? So the S starts off at 0 and goes up from there. The P's do the same thing. A P inside of a P, that's going to have one nodal surface, whereas the 2P, which is just, it's not inside of another one, it's just a double shape, that has nothing. And so they start with 0 and 1, 2, 3. The D is the same way. It starts with 0 and counts up 1 each time. They all are going to do the same thing. It's just where they start at. Well, they start at a different energy level because, again, the n equals 1 level, the first level, can only have an S, whereas the second level has both an S and a P, and the third level S, P, and D. And so they start at an increasing principal quantum number, and so do the nodes then as well.